Hello viewers, welcome to this next lecture on the NPTEL MOOC course on mathematical portfolio theory. You would recall that we had continued our discussion on the non-mean variance analysis in the last class, where you talked about semi-variance and semi-deviation, and you looked at the portfolio analysis while using semi-variance or semi-deviation as the measure of risk, and accordingly we also extended this in case of the capital market line and the security market line, again replacing the standard deviation with the semi deviation as the measure of risk. So, now in today's lecture and the next lecture, what we will do is that we will look at another important concept in the non-mean variance framework, and that is what is known as the stochastic dominance, and we will look at three forms of stochastic dominance. And today's lecture we will discuss in detail on the first order stochastic dominance. So, according to we start this lecture, on the topic of stochastic dominance criteria. So, this approach of stochastic dominance can be formulated in accordance with different utility functions, and you will explain this in details in the subsequent discussion. And accordingly, what we do is that we consider first, second and third order stochastic dominance. Okay, so let me start with today's discussion, that is on first order stochastic dominance. So, the first order stochastic dominance criteria. So, we observe that which in a sense competes and extends the paradigm of the Markowitz mean variance framework. So, we have extensively looked at the Markowitz mean variance framework, and now we are going to introduce the first order stochastic dominance, and this should be viewed more as some sort of extension of the mean variance framework, while at the same time competing with the notion of the mean variance framework. Okay, so the fact that stochastic dominance encapsulates or captures more information of the probability distribution instead of only focusing on the mean and variance. So, instead of just being restricted to mean and variance, stochastic dominance also focuses on capturing more information about the probability distribution. All right. So, this fact results in this approach to portfolio selection, namely stochastic dominance, becoming more potentially useful in determining portfolios that could outperform Markowitz efficient portfolios. Right. So, this means that if you take this approach of portfolio selection, it potentially could end up determining portfolios that performs better than the portfolios on the efficient frontier that we saw using the Markowitz mean variance framework. Now, this contrast, that means this difference between the stochastic dominance portfolio and Markowitz mean variance portfolio could become more visible or pronounced in case of non-normal distributions. All right. So, to motivate this, what you do is that now we consider an example. So, we take the probability distribution for 3 risky assets as given in the figure. So, let us look at how the probability distribution is going to look like. So, it is going to look something like this. On the x axis we have return as percentage, and on the y axis we have the respective probability. And then we consider, so let us consider the returns to be -10, -5%, 0%, 20%, 40% and 45%. Now, we take this portfolio A from -10 to 20%. We take portfolio B. So, this is going to be my portfolio A. Then portfolio B is something that is going to be from 0 to 40%. So, this is portfolio B, and portfolio C is something from that will go from -5 to 45%. Okay. So, here the distribution is assumed to be uniform, and we do this for simplicity of understanding, but the argument to be used subsequently can be applicable to other kinds of probability distributions. Okay, so now we have this uniform distribution. So, now you observe that in case of A, portfolio A, it is a uniform distribution lying in the range -10 to 20. In case of portfolio B, this is a uniform distribution in the range 0 to 40, and in case of C, it is going from -5 to 45. So, remember that for a uniform distribution, the mean is going to be A plus B over 2. So, accordingly, the return on portfolio A is simply going to be minus 10 plus 20 over 2, which is 5%. Mu B ranges from 0 to 40. So, this average is going to be 0 to 40, 0 plus 40 over 2, which is 20%. So, this is mu B, and expected return on C, that is mu C, this is going to be minus 5 plus 45 over 2, and this is also going to be 20%. And in a similar way, sigma A, remember sigma A is going to be square root of B minus A whole square by 12. So, this is going to be 20 minus of minus 10 square over 12. So, this is going to be equal to 8.66. Sigma B is going to be square root of 40 minus 0 square upon 12. So, this is going to be equal to 11.55%, and sigma C is going to be square root of 45 minus of minus 5 square over 12, and this turns out to be equal to 14.43%. So, mu A is 5%, mu B is 20%, mu C is 20%, sigma is 8.66%, sigma B is 11.55%, and sigma C is 14.43%. Okay. So, what do you do now? We will look at this in the mu sigma plane. So, let us consider a mu sigma plane. So, in the mu sigma plane, this is going to be the efficient frontier, and say this is your 5% and this is your 20%. So, this portfolio here, and on the x axis sigma is I take this to be 8.66%. So, this pair of 5% and 8.66%, this is going to be portfolio A, and then for 11.55%, and so I could have, so let me put this here, this is 8.66%. Let this point here be 11.55%, and let this point here be 14.43%. So, I take this 11.55% here, and the corresponding mu to it will be 20%. So, mu 20% and sigma 11.55%, this is going to be portfolio B, and the portfolio C is again going to be 20% value for mu with 14.43% for sigma. So, this is going to be my portfolio C. So, A is identified as the one with mu 5% and sigma 8.66%, B is the one with mu 20% and sigma 11.55%, and C is the one again with mu 20% and sigma 14.43%. So, this is basically portfolios A, B, C in the sigma mu space. Alright, so now what we are going to do is we are going to make a few observations out of this. So, here you observe that A and B lie on the efficient frontier. So, this means that these assets or portfolios A and B, these are mean variance efficient, and C, since it does not lie on the efficient frontier, so this is going to be mean variance inefficient. So, this means that in the Markowitz framework only A and B are going to be desirable, and C is not going to be desirable, because C is a portfolio that does not lie on the efficient frontier. Alright, so now this is one observation that we have made from the point of view of the Markowitz mean variance framework. The next observation that we make is that C, however, is more desirable than A in some situations. So, even though C is inefficient and A is efficient, even then C is going to be desirable, more desirable than A in certain situations. So, for example, to illustrate this situation, so what is going to be the probability that A earns less than minus 5%? This probability is going to be 1 over 6, but what is the probability that C earns less than minus 5%? So, that is going to be 0. So, you see the probability that C falls below minus 5% is actually this probability is less than the probability that A falls below minus 5%. So, that means that C actually is performing better than A in the scenario that the returns are falling below minus 5%. Now, another scenario could be that probability that the portfolio A earns less than 0%. So, in this case this is going to be equal to 1/3, but the same probability that C earns less than 0%, this is going to be equal to 1 over 10. So, again the probability that A earns the negative return 1/3 and this is equal to 1/3, and that is actually higher then the probability of C earning a negative return, which in this case is going to be 1/10. So, in terms of these are two specific examples where you see that under certain circumstances, if you set the criteria whether your portfolio return can fall below minus 5% or whether it can fall below 0%, in both the scenarios we see that C, even though it is not an efficient portfolio, but A is, even then C can actually be more desirable than A in that particular context. All right. So, one more observation that I want to make, and that is, so the third observation that I want to make here is that in case investors prefer more to less, C is more desirable than A, even though C is inefficient. All right. So, now let us look at what is going to be the cumulative distribution of asset returns for each case. So, remember that A is uniformly distributed in the range minus 10 to 20, B is uniformly distributed in the range 0 to 40, and C is uniformly distributed in the range minus 5 to 45. All right. So, let us identify this point. So, I have a minus 10 here, then I have minus 5, then I have 20, we have 40 and we have 45. And here on the y axis we have a cumulative probability, the maximum can be 1. So, for portfolio A, it's basically the cumulative probability will be this straight line from minus 10 all the way to 20. Now, in case of B, it goes from 0 to 40. So, the 40 is going to be here. So, from 0 to 40, the graph is going to look like this, and C is from minus 5 to 45. So, 45 is here. So, I start off with minus 5 and then I go all the way to 45. So, this is A, this is going to be B, and this is going to be C. So, this is the cumulative distribution. All right. So, now we can make some observation. So, you see that in the observation that for the range of possible returns for each case, the cumulative probability that the return of asset A is less than a specific return is greater than the cumulative probability that the return of asset C is less than the same specific return. So, what it means is that if you look at the entire range of values, then the cumulative probability, that means the value on the y axis, and you know that cumulative probability basically gives you the probability of the random variable taking a value less than or equal to a certain value. So, we take that to be the threshold value. So, if we fix a certain threshold value, then the probability or the cumulative probability of the returns being below that certain threshold level in case of A, and if you look at the cumulative probability of C of certain threshold, that same threshold, and you compare these two cumulative probabilities of the returns being below that certain threshold, you will observe that this cumulative probability in case of the asset A is going to be greater than that of the asset C, because you observe here that the graph A or the cumulative probability distribution always lies above C. So, accordingly we can say that this means that C is more desirable than A. So, because the probability of falling below a certain threshold is consistently higher than in case of A as compared to C, so obviously for that certain threshold the loss likelihood as given by the probability or the equivalent to the cumulative probability is going to be less in case of C, and that is why from a loss avoiding point of view C is going to be more desirable than your asset A. Okay, however, if you go back and observe carefully, so now you see that in case of A this is very clearly distinguishable in case of A and C, and in a similar manner if you compare A and B, so similarly B is more desirable than A. But since there is a intersection of B and C, so no such clear desirability exists between B and C. Okay, so now it is time to just recall the notation for cumulative distribution that you had obtained at the beginning of the course. So, the notation f of r, and I am using r to indicate that we are looking at the return random variable. This probability, so this is the probability that x less than or equal to r, and this in the continuous time framework, this is integral of f of x dx, which is where f of x is the probability density function of x, and the integral going from minus infinity to t. And accordingly, we now begin our discussion on first order stochastic dominance, so FSD, with an illustrative example. Alright, so now what we do is that we are going to look at the graphs of the probability density function. So, we consider first the graph of the probability density function and on the x axis we have the return and the y axis we have the probability. So, here we have the probability density function of B, and then we have the probability density function of A, and the corresponding cumulative probabilities. So, for that again we have the return on the x axis and cumulative probability on the y axis. So, on the top we have the cumulative distribution of B, and below that we have the cumulative distribution of A. Alright. So, now what you can do is we can make an observation here, that so you observe that here we have the distribution FB and FA, where FA is slightly to the right of FB, and consequently what you have is that the cumulative distribution of FB is consistently going to be at a higher level than the cumulative distribution of FA. So, this graphical representation of the specific case is something which will motivate our discussion on stochastic dominance. So, we now make the following observation, that the cumulative distribution for asset A, as you have already seen in the graph, this lies below that for asset B for any given level of return. So, accordingly it is said that asset A is more desirable than asset B in FSD, that is first order stochastic dominance. So, therefore, based on the premise or the assumption that investors prefer more wealth to less or more returns to than less, that is mathematically it is u prime of r greater than 0, asset A is said to dominate asset B if and only if, so it is a two-way condition, you have f A of r being less than or equal to f B of r as seen in the graph. So, that is f A of r minus f B of r being less than or equal to 0 for all r, and with the strict inequality, that is f A r being strictly less than f B of r happening in case of at least one value. So, at at least one point of r in the interval a b, the strict inequality must hold, and where your A and B represent the lower and upper bound on the return r, the random variable r, which is the return respectively. So, let us now give an interpretation of what we have discussed so far. So, the first interpretation is the following, that all monotonic non-decreasing rather utility So, I should write for all monotonic non-decreasing utility functions, that means where we have u prime of r greater than 0, the expected utility from A is no less than from B for all investors irrespective of their risk attitude. So, mathematically this means that the expected utility of all investors in case of the first asset or the return of the first asset. So, expected utility A of R is going to be greater than or equal to expected utility in case of B. And the second interpretation that you have here is that irrespective of the nature of utility functions being used, f A of r less than or equal to f B of r means that the expected return of asset A is greater than or equal to the expected return of asset B, that is E A of R is greater than or equal to E B of R. So, we now give the proof of FSD or the first order stochastic dominance. So, accordingly what we do is that we first identify the expected utility of each asset. So, the definition are as follows: the expected utility of return on the first asset, this by definition of expectation is going to be u of r into d f of a r in the interval a b. So, that is the range of your returns, and E of u of r b in a similar manner, this is going to be integral of u of r d f b of r from a to b, with f a and f b being the respective cumulative distribution with as I have said, the range of returns is a b. So, you have the cumulative distribution d f of a and d f of b, and then you have the utility u of r. So, the expected utility in the first case will involve this integral with respect to the cumulative distribution f a, and in the second case it is going to be with respect to the cumulative distribution f b. So, we now have settled down in what the expected utilities are in case of A and B. So, two generic portfolios A and B. So, now we come to what is known as the dominance. So, accordingly asset A is said to dominate asset B, and remember that this is in the context of FSD, and this domination is defined as if the expected utility of the return of asset A is greater than the expected utility of return from B. That is, in other words, we say that A dominates B in the sense of FSD if integral A to B of U of R. So, I am just using the definition of expected utility done previously, dFA of R, this is greater than integral A to B U of R dFB of R. That is, we can write this as integral A to B U of R into d of FA R minus FB R, and this is greater than 0. So, we can use either this form or this equivalent form. Alright, so now using integration by parts, what we will have? So, we will have U expected value of utility of R A minus E of U R B. This is going to be integral A to B U of R d of FA of R minus FB of R. If we use the integration by parts, so we see that so we will get this as the first function and we will take this as the second function. So, it is first function U of R into integral of second, which is FA R minus FB R in the range A to B minus integral of derivative of the first function, that is U prime of R, into integral of the second function, that is FA of R minus FB of R into dr, and this integral is from A to B. So, this is now simply going to be equal to. So, now here we just make the observation regarding this term. So, now since F A of B is equal to F B of B is equal to 1. So, remember that B is the largest value of the return. So, this it is the cumulative value is going to be equal to 1, and accordingly similarly F A of A is equal to F B of A, this is going to be equal to 0. So, this means that since this holds, therefore, the first term is 0. Hence, we can conclude that integral of A to B U of R d of F A of R minus F B of R, this is going to be just the remaining term after integration by parts. So, this is minus A to B, the integral of minus of integral A to B U prime of R F A of R minus F B of R dr. Now, since U prime of R is greater than 0 and F A of R is less than or equal to F B of R, and the inequality, strict inequality holds in one case, therefore, this integral A to B U of R d of F A R minus F B R, this is going to be greater than 0. And since this integral, you will remember this is nothing but expected value of U of R A minus expected value of U of R B, this is greater than 0. So, that means that it is because of this condition we have been able to arrive at this condition in terms of the expectation to show the first order stochastic dominance. Okay, so what I want to do is now I want to do another proof, and this is the proof for F A of R less than or equal to F B of R being equivalent to E A of R greater than or equal to E B of R for positive R. And we just make a note before we start the proof that replacing R with 1 plus R does not impact the argument. So, this is just to accommodate the case that mathematically R can be actually between 0 to minus 1 also. Okay, so in order to prove this, so we, without loss of generality, in order to prove this, we still assume R is greater than 0. So accordingly, we have the definition of E of R, and what is this going to be? It is going to be integral of R df of R as per the definition of expectation, 0 to infinity. Remember that your R is positive, and instead of 0 to infinity, we take that this integral from 0 to n with the limit that n tends to infinity. So again, using integration by parts, what do we get? So, we look at this integration. So, when you are doing integration by parts, so we will look at integral 0 to n of R df of R. So, I take R to be the first function and f df as the second function. So, it is first function R into second integral of the second function f of R from 0 to n minus integral of 0 to n of derivative of first function, which is 1, into integral of second, that is f of R dr. So, here this is going to be n into f of n, of course, the second term is going to be 0, minus integral 0 to n f of R dr. Now, what you can do is that we can add and subtract one term. So, that is minus n. So, I will have minus n minus 1 into 1 minus f of n, and accordingly here I will have plus 1 minus f of R dr integral 0 to n. So, you see here we from this term I will have minus n, and this integral dr of from 0 to n is n, and they cancel out. So, I add a minus n here and plus n here. Okay, now that we have this form, so let us now focus on this first term. So, however, n into 1 minus f of n, what is this going to be? So, this is going to be equal to n into integral n to infinity of f of R dr. Okay. So, this is 1 over f of n. So, it is 1 minus cumulative distribution from 0 to n. So, this means that this is 1 minus f of n is nothing but what happens from n to infinity. So, accordingly, this is going to be an integral from n to infinity of f of R dr. Now, you remember that here what we have done is that, so here we take the R as in this case, since the integral is from n to infinity. So, obviously, your R is going to be greater than n, that means n is less than R. So, then I can write this as integral, since n is less than R. So, I can write this as integral n to infinity R f of R dr, and this is going to be equal to 0 as your n tends to infinity. So, that means that we have been able to get rid of this first term here, and the only thing that remains is the second term. So, therefore, what I can say is that, so looking at the above relation, therefore, a limit n of 1 minus f of n is going to be equal to 0. So, this term is equal to 0 as your n tends to infinity, and hence the integration, this integration, which is the expectation of R, this simply becomes this expression as n tends to infinity. So, integral 0 to infinity 1 minus f of R dr. Therefore, this implies that if f a of R is less than or equal to f b of R, then we can use this relation to show that EA of R is going to be greater than or equal to EB of R for positive R. So, for this all you have to do is you essentially take this definition of EA of R and EB of R here, and you subtract them, and that will become the integral involving these two, and using this property you can show that this relation holds. Okay. So, in finality we have the following equivalent statements. One is that asset A dominates asset B in FSD. This is equivalent to the basic concept that FA of R is less than or equal to FB of R, where R belongs to some range AB, and this is equivalent to that the return of asset A is equal in distribution to return of asset B plus V tilde, where a random variable V tilde is greater than or equal to 0. And here I have introduced a new notation, equal superscript dist. So, this notation means that RA and RB plus V tilde are what is known as equal in distribution. So, let me conclude by one example to illustrate FSD. So, let us consider the probabilities of two assets A and B. So, let the probability and the returns of asset A. So, the returns could be 4, 5, 7, 8, each with identical probability of 1 over 4. And in case of asset B, the returns could be 3, 4, 6, 7, again each with identical probability of 1 by 4, 1 by 4, 1 by 4 and 1 by 4. So, from here what you get is we will get the cumulative probabilities. So, for this we have to look at what are the possible values of returns. So, the possible values of returns are 3, then we have 4, then 5, then we have 6, then you have 7 and then 8. And what is going to be the cumulative probability of x less than or equal to x? So, in case of A, what is this going to be, and in case of B, what is this going to be? So, in case of A, these values are going to be 0, 1 by 4, 2 by 4, 2 by 4, 3 by 4 and 1. And in case of B, this is going to be 1 by 4, 2 by 4, 2 by 4, 3 by 4, 1 and 1. Okay, so, now we have the cumulative probabilities for both A and B. So, now you observe that the cumulative probability of R A, all right. So, that means these values is no greater than that of R B, that is given in this column, for any value of return. So, observe carefully that here 0 is less than 1 by 4, 1 by 4 is less than 2 by 4. So, this is less than, this is so this is strictly less than, equal to, strictly less than, equal to. So, you see that in each case the cumulative probability is either strictly for A is either strictly less than that of B or is equal to that of B. So, that means that at under no circumstance the cumulative probability of A can exceed that of the cumulative probability of B. So, that means that if you draw the graph of capital F A of R and F B of R, then F B of R is always going to be either coinciding with F B of R or going to be below F B of R. So, in accordance with the first order stochastic dominance definition that we have already done, we can conclude that thus asset A dominates asset B in FSD. All right. So, this brings us to the conclusion of this lecture. In this lecture, what we did is that we started off extending the concept of the mean variance framework, and what we did is that we started looking at what is going to be the definition of the stochastic dominance, and we observed that the stochastic dominance can be of first, second or third order, and in today's class we just discussed the first order stochastic dominance, and we explained this from the point of view of that a portfolio A dominates a portfolio B if the cumulative distribution of f of A for asset A will be less than or equal to the cumulative distribution for the returns of asset B f B of R. And what we did is that we looked at two proofs in terms of the expected values and in terms of the utility. So, in the next class we will continue our discussion and complete the second order stochastic dominance and the third order stochastic dominance. Thank you for watching.